So we looked at an improper integral which arises when your range over which you're integrating is infinite or you have an infinite interval. The second one is if you have a discontinuous integrand. That f is a continuous function defined on a to b, remember, but not on b or not at b, not continuous at b. At b, it has a vertical asymptote, meaning it approaches this line but never touches. Right? That's an asymptote. Approaches but never touches. Then what we say is the integration a to b fx dx becomes integration a to t fx dx. So again, we use a dummy variable t, but we let t approach b from the t approaches b from the left hand side. B from the left side. So that's why we write it as t approaching b negative. For example, find 2 to 5 1 over root x minus 2. Now in this case, the fact that it's an improper integral has to be surmised by you. Now here you will observe that f of x 1 over x minus 2 has a vertical asymptote at x equals 2 because it makes the denominator 0. So we rewrite this as limit t going to 2 plus. Now why is it plus in this case? Well, it's plus because you're going from 2 to 5, and in this case the asymptote is at 2. Okay? So there's your t. T is approaching now from the right. That's why it's 2 plus. You carry on the integration, replace by t, and you end up with this limit, which is fine because as long as t is approaching from the right side, t minus 2 is positive. So the square root is well defined and it approaches 0. So this thing approaches 0. And I'm left with 2 square root of 3. Um, this is just an application of improper integral. Sometimes, we've already mentioned this many times, we are unable to find the exact value of integrals. In this case, what we can do is we can compare them to easier integrals to get bounds. Because the name of the test is comparison, we need to have two functions. F and g be the functions, and they're continuous, such that f is always greater than g for x greater than a. Then if f is convergent, then so is g. If g is divergent, then so is f. Roughly, why? F being convergent means it is some finite number L. So g is less than L, so g also converges. G being divergent means it is infinity, and f greater than g being infinity means f also diverges. Now important to note here, f is greater than g, right? And then the conditions are for when f convergent. If g is convergent, we can't say anything, right? Because f is still greater than g. Show that e to the negative x squared is convergent 0 to infinity. Again, this is an integral we have seen before. We've said there is no solution to this integral in algebraic forms. But we can solve and find values about these integrals. So first of all, I get rid of this infinity business. I go from 1 to infinity and 0 to 1. Because 0 to 1 is a problematic area, usually weird things happen, so I'm ignoring 0 to 1. Plus this is going to be finite from 0 to 1. Now 1 to infinity, when x is greater than 1, x squared is more than x. Negative x squared is less than negative x, because the inequality flips when you multiply by negative. E raised to negative x squared is less than e raised to negative x. So I let this be f and let this be g. So let's look at the behavior of f. It comes out to be convergent. So is g. So we know that g, this function, so is g, which in our case is e raised to power negative x squared. So that shows that the integral is convergent. Worksheet, find approximations T10, M10 for this function, estimate the error, how large does n be for accuracy to be. Show that in the formula, 1/3 of the trapezoidal plus 2/3 of the midpoint is actually the Simpson rule for 2n. Explain why these are improper. No need to evaluate. Important. Values of p for which x to the p ln x converge, similar to the problem we discussed before. Is this integral convergent or divergent? Show work. Okay, this is an improper integral because it goes to infinity, so you have to figure things out. That's it.